Assalamu alaikum dear students. Today we are going to discuss a new unit which is principle of mathematical induction, that is unit number 4. Now in mathematics we have to prove the mathematical statements, and there are number of methods to prove any mathematical statement. Now one of the method is the contradiction method. Now what is contradiction method? In contradiction method we usually assume with the given constraints or with the given conditions which are in the statement which we have to prove that this statement is not true. By using or while using the given constants after finite steps, we reach at a point where we get an absurd result. Absurd means like we get 1 equals to 2, which is absurd. So this means that this assumption was actually wrong, because we assume that the given statement is not true. So from this we conclude that with the given constants, the given statement is always true. So this is one of the method which is called as the contradiction method. Now the second one is the general proof through theorems, where we use the facts or we use the axioms and we deduce the result from in a stepwise manner. Like if we have to prove that we have to prove that 10 is even. Now we know that 2 divides 10 because 10 equals to 5 into 2. Now the second one is any number which is divided by 2 is even, because this is a definition of the even. So from this we conclude that 10 is even. So here in this method we follow the previous method, or we follow the previous facts, that is 2 divides 10, any number divided by 2 is even. So this means that here we are following the previous facts, or we are following the previous statements or steps. This is another way to prove this is the general method to prove in this theorem. Now there is another way, or the third way, which is the mathematical induction. For mathematical induction, firstly you should know the Peon's fifth axiom. Now Peon's fifth axiom states that let S be the subset of natural numbers. Let S be the subset of natural numbers. That is S is a subset of natural numbers with the properties that 1 belongs to S, because 1 is the natural number, S is subset, 1 should belongs to this. And if A belongs to S, that is A is any natural number in S such that its successor, which is A plus 1, belongs to S also, then this axiom states that this S is not only the subset, but this S is actually N. This set is actually N. So this means that this is not the proper subset, this is actually the improper subset, means this is set in turn, this subset is in turn a set itself. So this is the Peon's fifth axiom of arithmetics, or simply you can say that Peon's fifth axiom. Like now if we have a statement containing n means natural number, that is we have to prove a statement containing n. Like here we have a statement 1 equals to 1, 1 equals to 1, sum of first two natural numbers, that is 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10, 1 plus 2 plus so on to n is n plus 1 upon 2, n into n plus 1 upon 2. This means that here this is the general formula for this, that is sum of first n numbers is n into n plus 1 by 2. Now in order to prove this statement, that is we have to prove this statement sum of first n numbers is n into n plus 1 upon 2. We cannot prove this statement for each and every n, because there are infinitely many n's, or the set of natural numbers is infinite. So this means that we have to prove it with the fixed method, or with that method which contains the finite steps, because proof means to conclude the result within the finite steps. Now here we will use the Peano's fifth axiom. That is, we prove this statement for n equals to 1 because it is easy, because 1 is 1, first one natural number is only 1 and its sum is 1. So this means that this statement is true for n equals to 1, because if in equation first we put n equals to 1, it is 1 into 1 plus 1 upon 2. 1 into 1 plus 1 upon 2. And we assume that this statement is true for n equals to k, where k is any number, any natural number. That is, first sum of k numbers is k into k plus 1 upon 2. Then we use this assumption in proving for k plus 1. When we prove this for k plus 1 and it comes out to be true, then we conclude from the Peano's axiom that this statement is true for each and every n. True for each and every n, because 1 if for n equals to 1, if statement is true, and we assume that k for k this is true, and we use this assumption to prove for k plus 1, this means that the subset of S contains an element k with its successor within this S. This means that this S is actually n. Hence this is true for each and every n. This statement is called as the principle of mathematical induction. So principle of mathematical induction is used in those statements which contains n, and we say that the given, suppose we say that the given statement is p of n. That's we have to prove it for p of n. What is principle of mathematical induction? It is simply if a given statement is denoted by p of n, and we prove this statement for p of 1, and we assume in this principle we assume that it is true for k, and we again prove the given statement for k plus 1. When p of k plus 1 is also true, then we conclude that the given statement that p of n is true for each and every n. This principle is called as the principle of mathematical induction. Like we have to prove that the given statement which is sum of n numbers, which is denoted by p of n, is n into n plus 1. Here we are using the principle of mathematical induction. Here the given statement p of n is actually 1 plus 2 plus 3 up to n, that is sum of first n numbers. Now for n equals to 1, p of 1 is simply 1. P of 1 is simply 1, which is same as if we put here 1 into 1 plus 1 upon 2, that is simply 1, which implies that LHS is RHS, which implies that p of 1 is 1 into 1 plus 1 by 2. Hence this statement is true, means p of 1 is true. Now let's assume that the given statement is true for n equals to k. That is, p of k is actually 1 plus 2 plus k, because sum of first k numbers is k into k plus 1 by 2. Now this is assumption. Now we will prove this for n equals to k plus 1. Now p of k plus 1 becomes 1 plus 2 up to k plus 1, because if we have to find the sum of first 7 numbers, it is 1 plus 2 up to 7, then 7 plus 1, which is k plus 1 also, actually k plus 1. So it is 1 plus 2 up to k plus 1. Now from assumption 1 plus 2 plus up to k is because we assumed that this is true, which implies that this 1 plus 2 up to k is k into k plus 1 by 2 plus k plus 1. This is k plus 1. Now by cross multiplication, it is simply k into k plus 1 plus 2k plus 2 upon 2, which is k square plus k plus 2k plus 2 upon 2, or k square plus 3k plus 2 upon 2. Now splitting the middle term is 2k plus k. Taking k common from first two terms, it is k into k plus 2 plus 1 into k plus 2. Now again taking k plus 2 common, it is k plus 2 into k plus 1 by 2, which can be written as k plus 1. Now this k plus 2 can be written as k plus 1 upon 2. which is same as, now the given statement is P of n. We have to prove P of n is n into n plus 1 upon 2. Now P of k plus 1 becomes k plus 1 into k plus 1 upon 2. So this means that the given statement is true for k plus 1 also. Hence, by the principle of mathematical induction, we can say that P of n is true for all n. Hence, sum of first n numbers is, that is 1 plus 2 plus 3 up to n, is n into n plus 1 by 2. So this is the principle of mathematical induction. Inshallah, in tomorrow's lecture, we will discuss furthermore, the statements to prove the given statements through the mathematical induction. So thank you.